Okay, this section of the course focus on the mechanical design concept of overhead transmission lines with particular emphasis on sag and tension calculation. In power transmission systems, conductors are suspended between towers and their mechanical behavior under different conditions is very critical for both safety and reliability. You already saw some a part of the transmission line which was related to the reliability in my previous lecture. This part of the lecture introduced the fundamental concepts needed to understand how conductors behave when subjected to their own weight, environmental loads such as wind and temperature changes, and the forces acting on supporting structure and so on. So I will begin with an introduction to the importance of mechanical design in overhead lines, highlighting how um, your design can lead to excessive sag, calculate damage, or even structural failure. Then the concept of conductor sag and tension will be explained, describing the relationship between the downward curve of the conductor and the tensile forces acting along those conductors. So, following that concept, um, I want to study the calculation of sag, where mathematical models can be used to estimate the vertical displacement of conductors under various loading conditions. Finally, some basic mechanical principles will be discussed to provide the theoretical foundation required for accurate analysis and design. In overall, this section helps you to understand how to ensure that overhead lines maintain proper clearance, withstand environmental stress, and operate safety and efficiency. In general, as an electrical engineer, you will see electrical cable in anywhere in all of industrial applications. So this is also important topic. So this slide outlines the main topics covered in this section of the course on the mechanical design of overhead lines. It provides a clear roadmap of what you will learn, starting with an introduction that explains the importance of mechanical considerations in transmission systems. Next, the section focus on conductor sag and tension, which are key factors in determining how overhead conductors behave between transmission towers. And understanding the balance between these two um, concepts is very essential for maintaining safe clearances and preventing any mechanical failure. And the third topic is the calculation of sag, where we apply analytical methods and equations to estimate how much conductor will dip under different conditions such as weight, temperature, and span length. So finally, the section covers some basic mechanical principles which form the theoretical foundation needed to analyze forces, stress, and overall behavior of conductors in real-world cases. So, in general, this slide will give us a structure overview of the learning objective and prepare you for the detailed concept that we will discuss later on in the following slides. So this slide start to introduce an important concept in mechanical design of overhead lines, focusing on the role of tension in conductors when installing or uh, installing an overhead transmission line, it is essential to ensure that the conductors are maintained under safe and controlled tension levels. Sorry, 1 second. I will back. Um, okay, all right. Uh, okay, let me keep continue. Let me, sorry for any inconvenience. Yeah, if the conductor is stretched too tightly between the supporting towers, the internal mechanical stress will be increased significantly. And when this stress exceed the allowable limits of the conductor material, it can lead to serious consequences. In extreme cases, in the worst case scenario, excessive tension may cause the conductor to break, resulting in system failure and safety hazard and costly repairs and so many things. Therefore, this section emphasizes the need to clarify um, um, how we can balance tension during installation and operation, ensuring that the conductor remains strong, reliable, and within the safe mechanical limits. Okay, this slide explains how SAG is intentionally introduced in overhead conductors to ensure safe operation. And instead of pulling the conductor completely tight between supports, a certain amount of deep or curvature known as a sag is allowed. So we want to understand which amount of sag is acceptable. Okay. This design choice is very essential to prevent excessive mechanical stress in the conductor. So let's first start to define what is a sag. Sag is defined as the vertical difference between the level of the supporting points, such as towers, and the lowest point of the conductor. And by allowing this curve, the tension in the inductor will be reduced to a safe level, minimizing the risk of damage or failure. And in summary, we can say that SAG is not a flaw, but a necessary and control feature in overhead line design that helps maintain the balance between mechanical safety and reliable system performance. Okay, this slide is showing the physical configuration of an overhead transmission line and highlights three important parameters: span, sag, and ground clearance. You can see in this figure. The span is the horizontal distance between the two supporting tower. You can see this is a distance between two supporting tower. For example, in distribution level is usually 30 meter, and which determines the length of the conductor section due to its own weight. The conductor does not remain straight but takes a curved shape, creating a sag, which is the vertical distance between the lowest point of the conductor and the level of the support. Level of support is here. So this is a sag. So proper sag design is essential to ensure mechanical stability and to avoid excessive tension on the conductor. Finally, we have a ground clearance, uh, represent the vertical distance between the lowest point. You can see this lowest point of the conductor and the ground. This is ground, which is critical for safety, preventing electrical hazards, and complying with regulatory standards, especially if this is a very high, extra high voltage. So all of those things should be taken into account. Together, these parameters play a key role in the mechanical and electrical design of transmission lines. So we will see later how we can calculate it. Okay, this slide explains the behavior of conductor suspended between two EQ level supports, point A and point B, which means that both supports are at the same height. So in practice, the conductor is not pulled completely tight. Instead, it is allowed to lang under its own weight, forming a curve, natural curve like this, shape as catenary. We call this shape catenary. And the lowest point of this curve, is labeled as a point O, and the vertical distance between the support level and this lowest point is called the sag. From here to here, we call sag. So this sag is an essential design parameter, as it ensures that the mechanical tension in the conductor remains within safe limits while also maintaining adequate ground clearance. So the figure also hints at the tension distribution along the conductor, where the tension is a minimum at the lowest point and increase toward the support. So this is we call tension. Okay, this figure outlines several key mechanical principles of conductor suspended between two supports. First, the tension at any point along the conductor acts tangentially to its curve, meaning the direction of the force follows the shape of the conductor. And at the lowest point, um, I mean this point, O, point O, um, the conductor is horizontal, so the tension T0 acts purely in the horizontal direction. Another important point is that the horizontal component of the tension remains constant throughout the entire length of the conductor, regardless of position. So it can be, this is very important. So this is a remain constant entire the conductor. This is a fundamental concept used in transmission line analysis, and additionally, although the total tension at the support is slightly higher due to the inclined position of the conductor, its horizontal component is approximately equal to the tension at the lowest point. Therefore, the tension at the support T can be also considered approximately equal to T0, which simplify calculations in practical design. So we will have this one in practical design as well. Okay, this slide introduce conductor sag and tension, which are crucial consideration in the mechanical design of overhead transmission line. As I told you before, sag is the natural dip of the conductor between two supports. I already show you in the figure, and it must be carefully controlled. From an economic perspective, minimizing sag helps reduce the amount of conductor material required, and therefore lowering cost. So if we can reduce this sag, for example, up to here, it means that our conductor material will be reduced. This is very obvious, right? In addition, excessive sag would require taller support structure to maintain adequate ground clearance, which increase construction expensive. And however, sag cannot be reduced identically, um, and because decreasing sag results in higher tension in the conductor, which may lead to mechanical failure. Therefore, a proper balance between sag and tension is very essential to ensure safety, reliability, and cost-effective transmission line design. Okay, this part emphasizes another important design trade-off in overhead transmission lines. It is desirable to keep the tension in the conductor low in order to prevent mechanical failure or breakage, and to allow the use of um, lighter and less expensive support structure. So we need to find a compromise between these two parameters. However, there is a fundamental limitation. Low tension and minimum sag cannot be achieved simultaneously. So if the tension is reduced, the contactor will sag more under its own weight. On the other hand, reducing sag requires increasing the tension, so which raises the risk of mechanical stress and failure. Therefore, transmission line design allows involves finding an optimal balance between sag and tension to ensure that both safety and economic efficiency can be achieved. Okay, this statement explained in this slide the fundamental relationship between the sag and tension in overhead conductors. A low sag condition implies that the conductor is pulled tight, which results in high tension in the wire. On the other hand, if the tension is kept low, the conductor becomes looser and naturally exhibits greater sag due to its weight. So since these two requirements are in direct opposition, it is not possible to achieve both low sag and low tension at the same time. Therefore, in practical transmission line design, you always adopt a compromise between sag and tension, selecting values that ensure adequate ground clearance, mechanical safety, and economic efficiency. We will see all of those later on in this following slide. So first of all, calculation of sag. This slide is introducing the calculation of sag, which is I told you, an essential part of overhead transmission line design. So the sag must be properly adjusted so that the tension in the conductor remains within safe limits, ensuring mechanical reliability and preventing failure. So I told you sag and tension has a relation with each other. So several factors influence the tension in the conductor. The weight of conductor is the primary factor, as it directly determines how much the contactor will sag under gravity. Temperature variations also play a significant role, since the conductor expands in high temperatures and contracts in low temperatures, affecting both sag and tension. In addition, wind forces apply extra pressure on the conductor, increasing the effective load. In colder regions, ice loading further adds to the weight of the conductor, increasing both sag and tension at the same time. So, as a result, all of these factors must be carefully considered in sag calculations to ensure safe and efficient operation. Okay, this slide highlights that an essential design role in overhead transmission line regarding the mechanical safety and conductors. In practice, the conductor tension is intentionally limited to less than 50% of its ultimate tensile strengths to ensure safe and reliable operation under varying environmental and loading conditions such as wind, ice, and temperature changes. By maintaining this limitation, uh, um, you need to introduce an adequate margin of safety to prevent mechanical failure of the conductor during the service. So this concept is can be expressed through the safety factor, which is defined as the ratio of the unlimited um, final tensile strength of the conductor to its working tension, as you can see in this equation. So safety factor is equal to ultimate strength divided by tension. So a minimum, let me just add a new student. Okay, a minimum safety factor of 2 is typically required. So meaning the conductor must be able to withstand at least twice the maximum expected operating tension. So this is a minimum should be equal to. So it means the ultimate strength should be 2 times of tension. So this ensures long-term structural reliability and accounts for uncertainties in loading condition, material aging, and dynamic effects. Okay, in the analysis of overhead transmission line, the calculation of sag and tension in conductor is typically divided into two main cases based on the relative height of the supporting structures. The first case considers supports that are at equal levels where the conductor forms a symmetrical curve and the sag is identical on both side of the lowest point, making the analysis relatively straightforward. The second case involves supports at unequal levels where the conductor profile becomes asymmetrical and lowest point shifts closer to the lower support. In this situation, the sag and tension distribution become more complex and require additional considerations to ensure that the mechanical stress in the conductor remains within safe operating limits. Okay, this slide explains the behavior of the if a conductor suspended between two supports that are at the same elevation. So points A and B represent the supports. We have a support here or tower here, while point O is the lowest point of conductor forming a symmetrical curve. This is a symmetrical curve. This you can imagine that this is a mirror here. We will have a symmetrical curve. So due to the uniform distribution of weight, so because the supports are at equal levels, the SPAM is divided equally with one half of each side of the center. The conductor takes the shape of the um, um, catenary curve. As I told you, this is a catenary curve. We call catenary curve. And where the tension varies along the length, being minimum at the lowest point O and increasing toward both supports. So at any point P here on the conductor located at horizontal distance x from the O, so the vertical sag y and the weight component W times X influence the tension. So for example, for point P, if we want to find the tension here, the tension is if this distance is X, so and the height of the P from the O is equal to Y, so the weight component W and times X will give us a tension. This model is essential for understanding how mechanical forces act on transmission lines, helping you determine sag, tension, and overall stability of overhead conductors. Okay, this slide explains a key property of a conductor suspended between the two supports at equal level. It allows that the lowest point of the conductor lies exactly at the mid span. So this occurs because the system is symmetrical. Both supports are at the same height and the conductor has a uniform weight distribution. Okay, as a result, the shape and forces are identical on both sides of the center point. Okay, this slide also introduce important parameters used in the analysis. The span length L is the horizontal distance between the two supports. The term W represents the weight per unit um, uh, and length of per unit length of the conductor, which act downward and cause the sag. And T is the tension in the conductor, which varies along its length and is essential for maintaining the conductor's shape and mechanical stability. These parameters are fundamental for calculating sag and tension in overhead transmission line. Okay, this slide introduced the analysis of the conductor by considering an arbitrary point P along its length. The lowest point O is taken as the origin of the coordinated systems, and the position of point P is defined by the horizontal distance X and the vertical distance Y. You know, this is X and Y. So this uh, coordinate setup allow you to mathematically describe the shape of the conductor. So an important assumption uh, uh, is made to simplify the analysis. We have this assumption: the curvature of the conductor is considered very small. Because of this, the actual curve length of the conductor between points O and P can be approximated as equal to its horizontal projection. So in other words, the arc length OP from here to E, this arc length is taken as approximately equal to X. We can just approximate as up to equal to X. So this simplification is valid for most practical, um, easier equations for tension and sag. Okay, this slide also explains the forces acting on a portion of the conductor between points O and P. There are two main forces to consider. First, the weight of the conductor over the length OP, which is equal to W times X, acts vertically downward. This weight is assumed to act at the midpoint of the section. It means at distance X over 2 from point O. A second point is the tension T acts horizontally at the lowest point O. So to release these forces, moments are taken about point O, by equating the moments of the two forces, we can obtain that Ty is equal to Wx times x over 2, and which simplifies to this equation. So this equation represents a probabilistic curve showing that under the assumption of a small sag, the shape of the conductor can be approximated as a parabola, parabola curve. So this result is fundamental for calculating sag and understanding the mechanical behavior of overhead transmission lines. Okay, this slide also explains how the maximum sag or dip of a cable or flexible line can be determined under uniformly distributed load. So the key idea is that the maximum sag occurs at the midpoint between the two supports labeled A and B. At this location, the horizontal distance is equal to x is equal to L divided by 2. So, and the vertical displacement reaches its maximum values and denoted by S. So by applying the governing relationship for the cable profile under tension, the sag is derived as S is equal to this value. So which simplifies to this equation. So this equation also showing that the sag is directly proportional to the load intensity and W, load intensity W, and the square of the span length L, while it is inversely proportional to the tension T. So you can see in this equation. So therefore, increasing the tension will reduce the sag, whereas longer spans or heavier loads significantly increase the sag. So this slide want to introduce the case of conductors suspended between supports at unequal levels, which is a common situation in hilly or uneven terrain. So in such conditions, the conductor no longer forms a symmetrical curve between the supports. So as shown in this figure, so this is not uniformly or symmetrically. So we have sometimes the slope in the past. So that's why we cannot have symmetrical curve. So as shown in this figure, support A, we have two supports, support A and B. Support A and B are at different elevation, so causing the lowest point of the conductor level, this lowest point level O in different position to shift away from the midpoint of the span. So this asymmetry significantly affects the distribution of sag and tension along the conductor. Therefore, a more detailed analysis is required to accurately determine the position of the lowest point as well as the corresponding sag and mechanical stress. Understanding this case is essential for the reliable design and operation of overhead transmission line in real-world environments. Okay, this slide defines the key parameters required to analyze a conductor suspended between supports at unequal level. You can see we are in unequal level. The level of the support A and B are completely different. So the total span length L is denoted by L, while H represents the vertical difference in height between the two supports A and B. The lowest point of the conductor is labeled O, and its position is not centered due to the unequal elevation. The horizontal distance from point O to the lower support A and the higher support B are given by x1 and x2 respectively, you can see. And the conductor is subjected to a tension T, which plays a critical role in determining its shape and sag. As shown in this figure, the sag values at supports A and B are completely different, indicated by S1 and S2, reflecting the asymmetrical profile of the conductor. So these parameters from the foundation for calculating sag, tension distribution, and the exact position of the lowest point in uneven terrain conditions. Okay, this slide developed a mathematical relationship for a conductor suspended between the supports at unequal levels. Assuming W is the weight per unit length of the conductor, the total span is expressed as the sum of the horizontal obtained from the lowest point O to each support given by x1 plus x2 is equal to L. The general equation of the conductor curve is defined by this equation. So using this equation, the sag at each support can be determined by substituting the corresponding horizontal distances L to this equation at support A, where x is equal to x1, sag is equal to S1. And similarly, at support B, um, is equal to x2 and the sag is equal to S2. So these two expressions clearly showing that the sag at each support depends on the square of its horizontal distance from the lowest point, and you can see here x1 and x2, and leading to different sag value to the asymmetrical configuration. So you can see that the weighting and tension for both equation are the same. The only parameters can change the value of the sags for these two supports are x1 and x2. So this forms the basic for further analysis of conductor behavior under uneven support conditions. Okay, here if we can um, subtract these two sags together, we can have we just need to substitute the values, and S2 minus S1 will be equal to x1 plus x2 is equal to L, and S2 minus S1 is equal to H. So H is equal to, we just need to replace all of these equations, and finally x2 minus x1 is equal to this one, and we can find x1 and x2 based on the T, H, W, and L. I already defined all of this. H is here the difference levels between the support B and A. Okay, this is a new subject. This slide highlights the limitation of the basic sag equations and introduces more realistic operating conditions for overhead conductors. The standard sag formulas assume still air and normal temperature, where the conductor is influenced only by its own weight. So, however, in real-world scenarios, conductors are often exposed to additional environmental loads such as wind, pressure, and ice accumulation. Ice formation increases the effective weight of the conductor, leading to higher sag, while wind applies a horizontal force that can alert the overall loading condition. As a result, The conductor experiences combined loading effect where both vertical and horizontal forces must be considered to the result. And this not only increases the total tension in the conductor, but also changes its shape and mechanical behavior. Therefore, accurate sag and tension calculations must incorporate these factors to ensure safe design, adequate ground clearance, and reliable operation of transmission lines under adverse weather conditions. Okay, this slide explain how different environmental forces act on and overhead conductors and how they combine to produce the overall loading conditions. So the weight of a ice when accumulated on the conductor act vertically downward just like the conductor's own weight, thereby increasing the total vertical load. But in contrast,